Hi, my name is Amin, and I'm a graduate student at Columbia University. And today I'll be presenting my abstract in NeuroMatch called Controlled Switching Linear Dynamics, a framework for causal interrogation of neural networks. I also have to mention that this is a joint work with Laureline Logiaco, who is a postdoc at Columbia University. To quickly introduce the idea and our main framework, first I'll give a quick motivation. So in computational neuroscience, a fundamental goal is to build models that causally reflect the properties of neural systems. And by that, what we mean is that we want to build models and fit models that behave similar to the brain during the stimulation, not only for spontaneous activity and for stimulus-driven activity, but also when you inject some sort of perturbation into the system, we want a model to reproduce the observations. And to achieve this, we need to inject all different possible perturbation patterns and record the responses in response to those perturbation patterns. And this will allow us to build or fit a model that reflects perturbation properties of the systems too. However, this is computationally intractable simply because there is infinite perturbation patterns. Therefore, we need to pick the perturbation patterns in an elegant way that allows us to fit causal models without this computational intractability. So here is the approach that we propose. Instead of perturbing using all possible patterns, we first fit a switching linear dynamics to the observations from nonlinear systems. These nonlinear systems could be data from the brain or recurrent neural networks or other other nonlinear systems with analytical expressions. And once we fit a switching linear dynamical system to those observations, we know that the dynamics in each piece is described by a linear dynamical system. Now, we're going to use the fact that we have analytical expressions for linear systems that give us maximally informative directions for each of the linear pieces, meaning that we can find points in the state space that if we control the state of the system towards those points, they're going to maximally distinguish between the switching linear fit and the original nonlinear system. So we'll use this analytical expression, and we're going to find the input stimulus or input perturbation pattern that controls the state of the system towards those maximally informative directions in the linear state. But once we inject this input to the nonlinear system, this gives us a new set of observations. And by adding these new sets of observations to the previously recorded observations, we're going to be able to tune the switching fit to the system and make it more causal. So I'm going to walk you through the steps of our proposal for a toy model. Our toy example is Rustler nonlinear dynamics, as you can observe in the left side. So this is just a spontaneous activity from Rustler nonlinear dynamics. Middle plot is a projection of this nonlinear dynamics into 2 dimensions, x and y. And here we are focusing on a point, and we are showing the Jacobian or the linear approximation given by computing the Jacobian around that point. And then on the right side, we see this analytical expression that gives us the maximal direction, maximally informative direction of the evolution of this red point cloud. So we start from this red point cloud. We evolve this red point cloud according to some linear dynamics here given by the Jacobian, and each of these points will eventually go to another point, which is represented by this green point cloud, and there is a direction that has the most variance in the final point cloud. And that direction, we don't need to sample from the points. We know the analytical expression for that direction. Now, starting from this nonlinear observations, we're going to fit a switching linear dynamics to it. Here, I'm showing the switching fit with 2 states, and we can also sample from this fitted dynamics. And we can also visualize the two Gaussian autoregressive models that are fit to this nonlinear system. Here I'm showing the projection of those two Gaussians in the XZ dimensions, and here I'm showing the same thing in the XY projection, the XY dimensions. Now, based on this analytical formula that we have, we can find the stimulation pattern or the perturbation pattern that controls the state of the system in the linear dynamics towards the desired point that we have. And the desired point is just the maximally informative direction that we have the analytical expression for. So here we have four different iterations of our model. The green point is the point that we want to control the state of the system towards, and then the red is the controlled system, controlled linear system, and the black is when we inject the same control input to the nonlinear system. So ideally, if you have a perfect fit, we would want these to be on top of each other completely. But if they're not on top of each other, every time that we are finding this control law, we're going to add it to the observations and we're going to refit the model. So here is our augmented observation after adding these optimal or maximally distinguishing control laws to the system. So this is the augmented state space after injecting those stimuli, and these are projections of the state space into XYZ, and here is the control law that we are getting for those observations. We still haven't done the quantifications, but every time that we run this model, the fit to the switching linear fit to the system becomes more causal. So in conclusion, we developed a framework for efficiently finding perturbation patterns that distinguishes between our model fit and our nonlinear dynamics. And we also provided a recipe for tuning the parameters of the switching fit to the system to make it more causal. Thanks for listening.